All right. Hey, everybody. So in this video, we want to look at a more advanced limit. We want to try to rigorously prove that the limit as x goes to 2 of the expression x squared is actually equal to 4. Now, of course, we believe this because of our Calc 1 intuition, but I want to remind you that what we are really trying to prove is that for every epsilon, there exists a number delta such that if we plug in an x value that is in this range, meaning that it is within a distance delta of the number 2, but is not actually equal to 2, right? So the absolute value of x minus 2 is somewhere between 0 and delta. Then f of x minus L, aka x squared minus 4, is an absolute value less than epsilon. So that's what we rigorously want to show. And to show this, we know that we're going to start our proof as follows, right? So we're going to start our proof by saying, proof. We're going to start by saying, let epsilon be greater than 0. And then we know that we want to choose a delta in a prescribed way, take an arbitrary x value in this range, and show that if our x value is in that range, then x squared minus 4 must be less than epsilon. And we have to do a little bit of scratch work to figure this out. So I'm going to use the right side of the whiteboard, and I'm going to use purple to represent my scratch work. Now, the scratch work says that we know that x minus 2 will be in this range here. And what we are trying to show is that x squared minus 4 is less than epsilon. And we can do a little bit of algebra here. So we know that x squared minus 4, that's just equal to x minus 2 times x plus 2. Let me try to write it like this. That's x minus 2 times x plus 2. So that is the expression that will be less than epsilon. And what we would love to do now is we would love to be able to take x minus 2 to be less than epsilon divided by x plus 2, right? This is what we've done in the past with other scratch work. And we see that this would be really nice because we're assuming that we're trying to choose a delta so that we place x minus 2 in this range. Here we have an inequality involving x minus 2 and epsilon. So it would seem like at this point, what we might want to do is we might want to let delta equal epsilon over x plus 2. Now, unfortunately, we cannot do that, right? And the reason is that in the order of things, we start with our epsilon, we define our delta in a certain way, and then we allow x to be any value in this range, right? So x is defined after delta is. So we cannot actually define delta to equal epsilon divided by absolute value x plus 2 because x hasn't even been rigorously defined yet, right? X will just be a stand-in for any arbitrary value in this range. So this unfortunately doesn't work. And we actually want to end up erasing. I'll just scratch it out, but we want to scratch out / erase a little bit here. We want to go back to this previous stage. Actually, let's just go ahead and erase that. Yeah, perfect. Okay, great. So the trouble is really coming from this value, the x plus 2 here. And it turns out what we might actually want to do is try to come up with a bound on how big this can be, right? So what's the largest this can be? Right? What's the largest that could be? And because x isn't really specified, we can potentially worry that this gets really big. But we do know that we primarily want to look at x values that are close to 2, right? We want to look at x values that are in this range. So let's actually do something kind of sneaky. Let's set an absolute maximum value that delta can be. Let's assume that delta is bigger, that delta is less than or equal to 1, right? So delta will be less than or equal to 1. What does that mean about what our potential x values can be and what this quantity x plus 2 can be? Well, if delta is less than or equal to 1, and I'm only looking at x values that are in this range, well, that range is equivalent to saying that I'm only looking at x values that are within a range, right, of 2 minus delta up to 2 plus delta, right? Or in other words, boop, yikes, get our 2 back in there. Right, if this is our number 2, then I'm only really looking at numbers in this range right here. And so if my delta is guaranteed to be less than or equal to 1, then the absolute largest my x value could be would be a 3, right? Because all of my x values that I'm interested in are going to be between 1 and 3. And so if delta is going to be less than or equal to 1, then my x values will max out at 3. And then this quantity right here, the x plus 2 quantity, that will max out at 5. So we're going to know that x plus 2 is less than or equal to 5 in absolute value terms. So let me go ahead and rewrite this original expression. I'll write it down here. So instead of having x minus 2 times x plus 2 be less than epsilon, I'm going to point out that x minus 2 times x plus 2 will be guaranteed to be less than or equal to x minus 2 times 5, because that extra piece, that x plus 2, will be less than or equal to 5. And so if I guarantee, or if I make sure that that quantity is less than epsilon, so if we make sure, I don't quite know how I will word that, so I won't write that down, but if we make sure that this quantity is less than epsilon, then we would also guarantee that this whole quantity is less than epsilon, and that's really what we want, right? So ultimately, I can now make a choice to say that I want to make sure that x minus 2 is less than epsilon over 5, because if that is true, then I have that's true, which means this is true, which means that this quantity is actually less than epsilon as well. All right, so I have two things that I'm trying to pick, right? Or maybe I should say, so I want to make sure that since I want x minus 2 to be less than epsilon over 5, and I'm going to have x minus 2 be less than delta, I can try to set delta to be less than or equal to epsilon over 5. And it turns out we have two things that we're trying to satisfy now, or that two conditions that we want delta to satisfy. We want delta to be less than or equal to 1. That lets all of this sort of thought process make sense. And we want delta to be less than or equal to epsilon over 5, so that this makes sense. And with that, let's jump back to the actual proof. Let epsilon be bigger than 0. How will we choose delta? Well, according to our scratch work, we can say let delta be defined as the minimum of the two quantities we care most about. We want to make sure delta is less than or equal to 1, and we want to make sure that delta is less than or equal to epsilon over 5. So with delta defined in that way as the minimum of 1 and epsilon over 5, we can say that since, whoops, I want to say then, going back to our main structure of the proof, we can say let x be a number such that x satisfies this. And what we ultimately want to show, right, we want to show that x squared minus 4 is less than epsilon. Well, since we know that x minus 2 is less than delta, since x minus 2 is less than delta, and we know that delta is less than or equal to 1, we know that x minus 2 is actually less than 1, which means x is less than 3. And so x plus 2 is less than 5. Right, so here we're using sort of this assumption that delta is less than 1 or less than or equal to 1 to tease out this relationship here. Right, so x plus 2 is, oh my goodness, what does that even say? X plus 2 should say is less than 5. And since x plus 2 is less than 5, I think I should really throw absolute value signs over that. Right? So x plus 2 is less than 5. That will mean that x minus 2 times x plus 2 is less than delta times 5. And since delta is also defined as the minimum of 1 and epsilon over 5, I can say that this will definitely be true if I replace that delta with an epsilon over 5. And so we end up getting that exactly on the left-hand side, we get x squared minus 4. And on the right-hand side, we get that's a less than epsilon over 5 times 5. And so we get that x squared minus 4 is less than epsilon, which is exactly what we were trying to show. So, hooray. All right, I hope that helps out with this relatively challenging limit. I hope that makes sense. Thank you all so much, and I'll see you next time.